Okay, so my project is using the generalized Langevin equation formalism to reconstruct nonlinear dynamic equation from time series data. So this is the team mainly in collaboration with Michelle and also some one grad student, postdoc, and also a collaborator, external collaborator. So what I'm interested in is a very fundamental problem in science engineering, various fields. This is, when we study a system, this is a gene-regulatory network. So there are many components interact with each other. And we have similar thing in others, like stock markets, you have, or climate, all things. So you see, you have this interact with each other, many components. You need a lot of parameters and variables to describe the dynamics of the system. But the problem is in reality, you won't be able to monitor all of them. You only monitor a few of degrees of them. So you have very incomplete data. And the question is, how can we develop describe the dynamics of the system with this reduced degree freedom, given the fact that the whole system is very complex, highly connected, as Buddha just conceived the whole universe intricate, connected. The basic idea, when we study a system, what you usually do is you have degree freedom, you monitor them over time, you got some time series data, like this is single molecule enzymology, this is some spectrum. So one thing you do a time series analysis. From the previous known data, you get some mathematical equation try to predict what happened in the future. So linear time series analysis is very standard, have very developed. But nonlinear dynamics, nonlinear time series analysis, still underdeveloped field. So people don't know how you define this nonlinear equation form. What I specifically one problem we got in mind is this. Okay, think about the brain. About 100 billion neurons interact with each other. So when you measure EEG, what you do is you have few number of electrodes. Try to monitor a few neuron or area of neuron their activity. What's shown here in the typical data for, in this case, the patient has some, first normal, then got some seizure. So seizure is a serious condition. You have to get it back as quick as possible, otherwise kind of lethal. So one way a doctor, what they do is they apply some electric shock on the system. But they don't know really how it works, how to apply it. It's just randomly. It's art. So they hope it can work. So I talked with this neurologist, David Hsu, and you see, Wisconsin medicine. Interestingly, his background is he got first a PhD in chemical physics, as I got, then got an MD, become neurologist. So we will feel, okay, this system from a chemical physics field, like a ball moving in a high-dimensional surface. So if we know the equation of motion of the system, then we'll know how we apply external force, help with the jump from this metastable state to this state. If you just don't know it blindly, it may help you try to push this way or push the other way. It may be things worse, right? Okay, so that's to give you an idea. We need to go to this dynamic equation. In statistical physics, we have a well-developed method called Moritz-Zwanzig projection method. The original idea goes back to Einstein in his magic 1905 year. He worked on Brownian motion, then formulated by many prominent theoreticians like Langevin. In 1960s, Bob Zwanzig, he gave a formal derivation. Then, after several years, Maury gave the linear version. Okay, so this is what happened in statistical physics. Then, in recent years, a lot of interest try to apply in a general dynamic system, especially led by Alexander Chorin at UC Berkeley. He is a very prominent mathematician, National Academy member. So they have tried hard to apply to general dynamic system with limited success. While I was still at Berkeley, I got this idea, heard of this, so I got interested in this. It took me quite a few years to work out the math. I'll give you the idea later, but the general idea, I'll give you a simple case. So what is shown here is a protein interaction. So, but you experimentally only measure the distance between these two residues, although they interact in remindings. But from the data, you can use some kind of this kind of differential, this equation to monitor, to describe dynamics of this reduced dimension, taking account its interaction with all the remaining degrees of freedom. Okay, so what's the basic idea? Let's think about, let's say a simple case. You're working, let's say 3-dimension, you have some motion in this 3-dimensional world. But somehow we only live in a 2-dimensional or 1-dimensional world. So we can only monitor in this reduced dimension. But from the dynamics, you should be able to describe the effect on this hidden degree freedom. Okay? The math is like this, we start from a stochastic differential equation after very tedious derivation took me several years. Well, anyway, and the end is this. So you have some resolved degree freedom, which is a subset of the full degree freedom. Then you end up this equation motion, which W is related to a stationary distribution, and this M and K is the memory kernel, taking account the interaction between your primary degree freedom and the remaining degree freedom. So then you have a random noise which relate to the magnetic kernel to this fluctuation dissipation relation, first noticed by Einstein in a simple special case. Okay, so this is the mass. Then how can we apply it? You have this dynamic equation. First, you do ensemble average over this stochastic noise. You got this equation. And now here's a key point. You describe this. All these terms in the bracket can be captured from your data. Then you only leave a linear equation for this M and K. So you can solve out M and K, then F. You reconstruct your dynamic equation. And also, I told you the nonlinear time series analysis is very hard to work out the form of nonlinearity. And here, all the nonlinear characters come from W, which is related to stationary distribution. You can just get from the data directly. Okay? So we have some tests, but I only show you one example. So because first we want to test some known system, so we can handle so we just took a model from my colleague John Tyson, the model cancer dynamics. So there's some interactions there. Don't worry about those. But the key thing, there's one thing, GFR, that supposedly we can monitor experimentally. Then John has this full model, so you can run simulations, you mimic this experimental condition, you have the time series of this. Then we say, from the procedure, we run full model simulation, and we run this, can reconstruct the general Langevin equation. So this is the dynamics of GFR simulation and the full model. We see the degree quite remarkable well. This one shows you, the system has some bistability. So you start from this stage, you go to this stage. We want to look at this transition first partial time distribution. So that's the key thing why we use this you have some long-time dynamics. Once you reconstruct dynamic equation, you can predict long-time behavior. And indeed, you see, this is very challenging to get this distribution right, but the degree is remarkably well. We have some other examples, but I won't show here. But the key, let's make a summary. See, it took a while to work out the core numerical algorithm. I show you it looks very simple, but numerically it's very challenging. Deal was we have to find out some way tricks to make it stable, and we test on some model system. So now we got the data. Now we got data from real EEG data from collaborator. So we are analyzing it, and we hope this will form some preliminary result for some proposals. And then a key thing, we form an interdisciplinary team that can help to do this. We have one paper in preparation, so we hope the student give me the final thing we should submit soon. Then we have some other manuscripts we expect to follow up quite soon. We have several proposals in mind. Actually, I already submitted one to James McDonald Foundation on this. We also think about DOE on the applied math division and some other funding agencies. I have been given talk on this subject on several invited seminars, like UNC Chapel Hill Applied Maths Department, Wisconsin Medicine, their theoretical chemistry seminar series, and some other. I'll give another one in Peking University this summer. The key thing is, I met this person in Wisconsin Medicine. He is a neurologist, something or expert necessary for us to really apply this to some real system. So this is a very short summary of this project, and seems I'm very quick, right? Okay.